be recording this portion of the work, and if you have a comment, it will be included, or a question, it will be included. And just to let you know. Now, I just want to check in with our picture of the atom before I do the first homework, because what we're going to be doing is we're going to be putting electrons in atoms, and our picture of the atom based on the quantum mechanics that we've done is that first off we have an atom. Well, let me just draw this big. And if we put the nucleus at the origin, then our picture of the atom is that there are principal energy levels, and these principal energy levels are designated by the letter n, so that's a lowercase n, and the first one is n equals 1, and then it's n equals 2, and these are supposed to be circles, and the circles of course represent three-dimensional spheres. But our picture is there's n equals 1, n equals 2, n equals 3. And I'm going to put dot, dot, dot here all the way out to n equals infinity. Okay? So there are quite literally, and I don't use that term lightly, an infinite number of n values, and they just keep getting bigger. Okay, and the thing about n equals infinity is the state where the electron has left the atom. And we typically don't say where that electron goes. All we know is that as far as the atom is concerned that we're talking about, the electron is left. Okay, and our picture of this is further enhanced by the fact that, let's say this is a hydrogen atom. And for the hydrogen atom, we will be talking about electron configurations, and the hydrogen atom has an electron configuration of 1s1. And what that means is that in the n equals 1, there is an s sublevel. So n equals 1, s sublevel has one orbital that can hold up to 2 electrons. And so the most you will ever see, or the biggest number you will ever see as a superscript here, is going to be 2. And that's because that's the maximum number of electrons that an s sublevel with one orbital can hold. And for hydrogen, it's not full. There's only one electron in it. And so our picture of the atom for a hydrogen atom here might put an electron in n equals 1, and n equals 1, we would also call that the 1s sublevel. Okay? Are there any questions so far? There's more to say, of course. Okay. Well, so then when we go, okay, so let me say this actually before I move on. So as this electron moves away from the nucleus, and let's go ahead and do that in a third color. We'll choose red this time. As the electron moves away from the nucleus, I think we'll put it up here. The atom absorbs energy because the electron is going to a higher energy state farther from the nucleus. So as the electron moves away from the nucleus, the atom absorbs energy, And typically the way that it absorbs energy is, and this is certainly the calculations that we do, is that it absorbs energy by absorbing a photon of light. Okay? And some other terminology we're going to run into today is that when the electron is in n equals 1 for hydrogen, that's what's called the ground state, which is the lowest energy state. And when the electron moves to a higher energy, it's called the excited state. So, and the excited state is any energy level that is higher than the ground state. So if the electron moves from n equals 1 to n equals 2, that's an excited state. If the electron moves from n equals 1 to n equals 3 or 4 or 5, those are excited states as well. So there are many excited states. There's only one ground state. Okay. Okay, so then that's our picture. We're going to add to it. And let's see if I can keep both of my pictures and the whole page on screen. Okay, so for n equals 1, there is only an s sublevel with one orbital. But as you go to n equals 2, and I'm going to try and make it's approximately the same size as above so we can compare. So to the n equals 2 up here. And I'm not going to make n equals 1. Well, we'll say limited success anyway. But so in n equals 2, there is a 2s sublevel with one orbital. And then there is a 2p sublevel with 3 orbitals. And the 2s is just like the 1s in that it can hold a maximum of 2 electrons. And in fact, the only difference between the 1s and the 2s is their size. But now let's talk about the 2p. And I guess I'm going to do my 2p's in green, the 2p sublevels, with 3 orbitals. And those 3 orbitals are called 2px, 2py, and 2pz. And in order to determine which one is which, we are going to call this the x-axis. And I don't know, I need a better green. Let's see if that one's better. Nope. All right, we're going to stick with this one then. Okay, so on the x-axis, we can draw the 2px orbital. And when we draw it, we are not going to touch the nucleus. And we're going to draw sort of 2 balloon shapes. 1, 2. And what's important when you draw these is they're sort of like circles and that they end where n equals 2 ends. Because the idea is that the 2s and the 2p sublevels, or let's say this, the orbitals in the 2s and 2p sublevels end at the same distance from the nucleus. So I'll make this note down here. So the orbitals in the 2s and the 2p sublevels end at the same distance from the nucleus. And distance from nucleus. Okay. And I could do the same thing on the y-axis. And I guess I'll do the y-axis one in red. So 2py is going to be the same shapes. Well, attempt to draw the same shapes, except on the y-axis. So I'll write 2py and 2px. Okay, and I think that's all I wanted to draw as far as diagram. So I guess I could draw the 2pz, but 2pz comes up out of the page and goes down below the page. So that's a little tricky to draw, so I won't. It just clutters the diagram, I think. But the idea is that for n equals 1, the space or the volume is small enough that you can only do a total of 2 electrons. And those are the 1s electrons. But n equals 2 is bigger, and n equals 2, you can do 2s, which is a sphere, and you can do 2p, and the p sublevel and the orbitals in the p sublevel are other higher energy ways of putting electrons in the same space. Because of course, the electrons being negative are attracted to the nucleus, which is positive. And so the electrons want to be as close as possible to the nucleus, except that electrons are also repelled by the other electrons, so they can't all be as close to the nucleus as possible. So that is what I wanted to say for the model of the atom. And then I guess the last thing I'll say is for n equals 3, there's even more space, even more volume. So in n equals 3, there will be 3s, 3p, and 3d sublevels. And 3d sublevels have 4 parts, and there are other ways of sort of sliding electrons into the same n equals 3 circle. And it just gets harder and harder to do it, so the shapes get more complicated. Okay, so that's sort of background. Any questions about this picture of sort of how we're going to do electron configurations and how the electrons fit in the atom? Okay. All right, so then now let's start attacking the homework questions. So for the homework question, this is the first homework question, and it says write a ground state electron configuration, and it says complete, no abbreviations or noble gas cores, and we'll talk about what that means in a minute. It just means you have to write everything out of an atom of, and it says strontium. And now we're going to turn to our periodic table. And the way that I do electron configurations is I look at my periodic table. I start at the very top. The periodic table is actually broken into S areas. And S areas have 2 elements because it's 1s2. And it's true that helium's over here on the other side, but some periodic tables also put helium here because, and we'll see why. But 1s, and then you get to the end, and then you come back and you're ready for the 2s area. And so it'll be 2s, 2p, return to other side, 3s, 3p, 4s, and so these are always the s areas. These are always the p areas, and these will always be the d areas. And what we'll see is complicated is first the 4s area comes before 3d, so the numbers go back 1 here. Anyway, so you will have a periodic table. I suggest that you learn how to do electron configurations by looking at the periodic table. And so here's what we're going to do. as I write this out, I'm going to be doing it for strontium. Strontium is element 38. So we have a strontium atom. And what we know from the periodic table is that since it's element 38, there are 38 protons. And for atoms, atoms have no charge, which means that the number of protons must equal number of electrons. So that's how I got 38 electrons. And from there, I'm going to start up here. I'm going to do 1s. The 1s will hold 2 electrons. Ding. Then I come back. The ding sound is I'm imagining I'm a typewriter that gets all the way to the right here and then has to return to the left. I realize that reference may be a bit dated, but there you go. Now I'm in the 2s area. So I write 2s. It's 2 elements wide, so I write 2. And now I've put 4 electrons, and I've effectively finished here. So now I'm going to jump over here. This is the p area, specifically the 2p. It is 6 elements wide because p sublevels hold 6 electrons. Now I'm at 10 total electrons, and I've gone through element 10 on the periodic table. Ding, head back to the other side. Now I'm in the 3s area. 2. Keep going. So 3p, 6. Ding, return to other side. Now I'm in the 4s. Here's where things get tricky. So after 4s, you go back to 3d. The 3d portion of the periodic table is 10 elements wide. That's because a d orbital holds up to 10 electrons. All right. So again, you can count up the number of electrons. You'll find there are 30 electrons in here so far. We're effectively right here at element number 30. When we go to element 31, we're in the p area. This is going to be 2p, 3p, 4p, and it holds up to 6. Ding, return to other side. Now we're in the 5s area, and it holds 2 electrons. We're at strontium. If we count up all these electrons, which are the superscripts, we will see that they are 38 electrons. Now, when you enter it in, we don't take superscripts, so you're going to be entering it as 1s2 space 2s2 space 2p6 blah 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 blah, and I can't help it. I keep making the superscripts. There we go. So we won't do superscripts. And so just all sort of regular. I don't know if answers take superscripts anyway, so I don't think you can actually do it. I don't know though. Now, yeah, so I think so, ... But this is the answer, and you're going to just enter it not as superscripts, just as regular numbers with spaces in between each one. That's what this portion means here. Enter the entire electron configuration with one space between each sublevel and no superscripts like this.